Okay, guys, quiet. Let me talk. Thank you. All right. So for number one, those are not equivalent vectors. So to find the component form of the vector, if you're given an initial point and a terminal point, it's just delta x and delta y. Delta x is terminal minus initial, right? So you take the x2 minus x1, the second x coordinate minus the first x coordinate. So you have a starting point, and then the arrow goes toward the starting point. So you always want to do where the arrow is pointing to minus the initial point. Do it for both x and y. You get that for u, you get that for v. Obviously, those are different values. Now, the one interesting thing is they have the same magnitude. They both have magnitude of root 73, but one is going the opposite direction. So, yeah, they're not equivalent. B, they are. So great, find those equivalent vectors. Even if they start and at different places, they're parallel and they have the same length. As long as they're parallel, same length, and the same direction as well. Because it could be this way and that way, and that's not okay. For number two, the double absolute value means magnitude. So it's just like Pythagorean theorem or distance formula. That's pretty easy. So two should have been fine. And so for A and B, not a problem there. B's a little crazy with the fractions. Deal with it. For three, those are operations for vectors. So like scalars, kind of like distribution. So if you put 1/2, then you're actually making it shorter, making it half as long, right? If you're adding vectors, from a geometric standpoint, as I mentioned during class Tuesday, if you draw both vectors, now what you could do is draw the first vector, the second vector, connect it to the head of the first vector, and just go whatever direction you have to go. So like in this case, I have to go 4 left and 3 up. So after I draw the first vector, starting at the origin, so you can always start any vector at the origin, it's totally fine. But then we want to connect the second vector to it. Start at the end of the first vector, go 4 left and 3 up to draw that second vector. Then the connection between those two vectors is the addition of them, right? So if we think about it, if I connect the tail of the first vector and the head of the second vector, that's u plus b. So that's geometrically what's happening, and it does confirm the arithmetic here, right? So arithmetic shows -5 comma 0, and the geometric representation is also -5 comma 0, right? It is going 5 left and no vertical change. So we can geometrically imagine, oh yeah, let's draw that one vector, then let's do the other vector in that direction. And we're gonna do a word problem today involving an airplane and wind speed, and that should hopefully make more sense of why these vectors act the way they do. It's kind of like, what if you have a boat or an airplane and there's a wind or current blowing in a certain direction? Of course, it's going to blow you in a certain way, right? Or move you a certain way. So that's kind of what's happening when you combine the vectors, you get a final result. So we're going to talk about that today. Now for subtraction, treat subtraction like addition. What you're going to do is v minus u is no different than v plus negative u. Think of it like that, right? Like if you have 6 minus -5, that's 6 plus 5, right? We know that. Or if 6 minus 5 is 6 plus -5. So same thing here. -4 comma 3 minus -1 comma -3. We'll draw a b, not a problem. That's easy. Go 4 left, 3 up, we're good. Then what you do is you look at u. If I were to draw u from over here, I have to go 1 left and 3 down. So it looks like that, right? That's u right. Sorry, that's u right there. I don't want u. I want negative u. So I want v plus negative u. So what do I do about this u? I rotate 180, like that. So now if I add this with this, that is v plus negative u. So I connect tail to head, that's v minus u. So it's the same kind of thing as addition, just you have to reverse it. If you treat it that way, you'll be fine. And of course, these scalar with subtraction, whatever. Just increase the length, and of course the -3, the 3v, just reverse it and you're fine. Because if I were to do this, if I were to go 12 right, so here's 2u. If I go 12 right and 9 down, actually, sorry, 12 left, because initially it's -12, -9. So if I were to go 12 left, no, sorry, I meant to say positive 9. My apologies. If I shoot it to 3, that's what you're supposed to get. So if I were to go 12 left and 9 up, it's supposed to look like this. But when I reverse a 180, then I get that. And then, of course, you connect tail to head. Keep moving. Number 4. IJ stuff is the same thing as component form. I is for X, J is for Y. Very easy. Magnitude, easy. Unit vectors, you take the components and divide by the magnitude, and you can simplify afterwards. I personally don't care if you rationalize the denominator. I don't care. You can if you want. Why do we have unit vectors? That's so we could scale down to a length of magnitude of 1. That's why we have the unit vector. For 5, same stuff, not that much different. 6, right in terms of I and J, it's all good. 7, that's fine as well. So shouldn't be was 5, 6, 7 pretty straightforward. No issues, yeah. For 8, so direction angle, I don't know if we talk about that? We didn't, yeah. Okay, so if you're stuck on 8, we're gonna talk about that very shortly with the notes today. So if you think about it, cosine goes with X, sine goes with Y. We know this already. So what if, for example, so you know the magnitude is 3, right? The magnitude is 3, but there's a certain direction that goes with it. So here's what's happening. This vector is pointing like this. That's 143 degrees. So how would you figure out the horizontal and vertical components? That's a horizontal component in blue. That's a vertical component in red. How would I do, and if I call this X and call this Y, how do I determine X and Y? Well, we kind of know this already, like from unit circle, right? We know this from unit circle that if you do, this is theta, right? Cosine theta is this over this, right? Or in this case, cosine 143 is X over your radius or hypotenuse. And then sine is going to be Y over that, right? So yeah, that's all you're doing to figure out the horizontal components. That's all you're ever doing. Because you're doing the magnitude times the cosine of the direction angle to get the X coordinate of the vertex. So sorry, of the vector. And to get the Y coordinate of the vector, you got to do the magnitude times the sine of the angle. For 9, again, more of the same stuff. You have the magnitude, get the unit vector, and of course, we have to multiply by 3. So my God.
I did that, but I just don't know what.
Actually, look at the instructions. Yes, that's a great question because I forgot the instructions. That was not very clear. Let me explain that. Yeah, so here's what's happening. You want a magnitude of 3. They want that. So right now, the magnitude of this vector is 13. So I do Pythagorean theorem.
Okay,
That's what we do, right?
right.
12 squared plus 5 squared is 169, 169, 13. I want to get down to 3. So it might be easier for me to scale this down to a magnitude of 1 by doing a unit vector. Because we know the unit vector is when you take these components and divide by this magnitude. And so once you have down to a unit vector, what's the magnitude of that? 1, then multiply that by 3 to get to magnitude of 3. So you use the unit vector as a bridge. That's what you gotta do. Yeah. And then finally for 10. So if you think about where that vector is pointing, that vector is pointing in the 3rd quadrant. However, when you do inverse tan of 5 halves, it's going to be answered in the 1st quadrant. I don't want the 1st quadrant. I want the 3rd quadrant. And as you know, tangent is positive in Q1 and Q3, tangent is negative in Q2 and Q4. So if you have an angle in Q1, what will be its equivalent angle in Q3? Just add 180, right? It's going to have the same ratio, right? Because you're going to have the same height and same base of the triangle. So it's just going to be the same thing. Just add 180. Even if you're in Q2, just add 180. It doesn't really matter. Q4. So that's the direction angle. So you have to make an adjustment. And of course, magnitude's easy. That's just Pythagorean theorem. So, or distance formula. So hopefully that makes a little more sense. We're going to talk more about this in the notes today. Nadia, go. Oh, sorry, say again. If it's positive, this negative is going to be Q4. Remember the default range. This goes back to several units ago. The default range from negative pi over 2 to pi over 2. So if it's a negative ratio, you're doing inverse time a negative number, that's going to give you a Q4 answer. But it's a negative angle. So then you got to adjust it depending on where you are. If you want to be between 0 to 2 pi or 0 to 360 and give you a negative answer, just add 360 to it, right? That's what you do. Or does that make sense? Yeah, 360, right? Because you're just going around to the same place. But if you want to be in Q2, then add 180. Yeah. We'll talk more about that today. So yeah, hopefully you guys are okay with that. Yeah, B was a Q4. So it gives you a negative answer. Actually, that's weird. Why did I put 6/1? That's weird. I was just done inverse tan of -6 and just add 360. That's dumb. Anyway, we'll move on. Yeah, it's
But that's the right answer.
no, that's the right answer, but I just don't wait, hold on. Yeah, just add 360. It's the same thing. It's the same thing.
270 plus the angle.
No, because it's supposed to give you negative 80.537. Add 360 to it, gets 279.462. That's the same thing as adding 360 to negative 80. Yeah.
But you can find the like angle along the.
You could do that too, sure. Sure, you could. Yeah, you could. All right. And there was also a part C as well. It's more the same stuff. So, okay, guys, let's go to the notes. Let's finish off the notes on vectors. Here we go. Okay, please remind me, where do we leave things?
To the last page, or direct angle.
Okay. Yeah, I think I remember I was like sitting down teaching it. I was like so out of it. Yeah, I'm so much better today. All right. Okay, so I'm gonna be more live with you guys today. Good. All right, so do we do example 5? Yes. And 6? Okay, so let's start with that. Let's talk about direction angle then. All right. So direction angle of a vector u is the angle measured counterclockwise from the positive x-axis to the vector u with initial point at the origin. And guys, Samar, let me talk. Thanks. In context of vectors, direction angle is often measured in degrees. Okay, so we use degrees. So if you want to do -6, 6, it would look kind of like this, right? That's a -6. That's a 6. And the angle look like this. Now, just using basic right triangle geometry, I know it's 135 degrees. How do you think I know that?
45, 45.
Exactly. It's a 45, 45, 90 triangle. When I try to connect this with this, here's X, here's Y, right? Clearly, I know I'm gonna have a 45, 45, 90 right triangle, right? So fine, whatever. But what you really could do, because we'll need to do this for part B for sure, what you could do as a universal way is tan theta will equal delta y over delta x, or -6, sorry, 6 over -6, which of course is -1. So theta will be the inverse tan of that. Now, if you know your unit circle, the default range from -pi/2 to pi/2, we're going to give this in degrees. That's going to be -45 degrees. But I don't want -45. That's in Q4. I want Q2. You add 180. Because you got to rotate 180. Right? You have to add 180. You have to rotate halfway. Q4 is what is spit out, but I want Q2. So that's what I want. So I'm going to do the same thing for part B. What quadrant is that point again?
2.
3.
3.
Right? Okay. 3. The quadrant. Right? -7. -4. No worries. I know you guys got this. Just firing too fast. That's all. That's all. Just take your time. Be patient. Vectors require patience, guys. All right. So, well, most of math does. So -7, -4. Now, I expect the answer to be more than 180, less than 270. But I'm going to do tan theta is -4 over -7, which of course is 4/7. And I got to do the inverse tan of that, which is obviously not a number I can easily do in my head. Actually, I can't do in my head. So let's see what it spits out. It should spit out inverse tan of 4/7. I got to switch to degree mode. I got 29.745 degrees, but add 180. Nope, degrees. We don't do radius of the stuff. Yeah, what's up?
Final, we're gonna have to switch it from radian to.
Oh, I got you guys. Hold on a sec. Okay. Yeah, listen. I'm talking about the final, guys. All right. On the final exam, I think, I'm not 100% sure, but I think I do state for every problem whether you should be in degree or radian mode. I think I do that
Be made.
from last year. Yes.
What else is in your rating?
So.
You
Yeah.
just put it all in degrees?
No, it's polar.
No. I have to put some things in radians also. Yes, guys. Arnold doesn't listen. I know. You know what? He doesn't have to know. Everyone else knows except for Arnold. So that's good. All right, let's keep moving. All right. Okay. No. I think I do state for each problem whether you have to be in degree or radian mode. I think I do. Yeah. So
Split up to 2 tests, one in radian, one in degree. That's looking a good idea.
no, because some has to be calculator. So, no. She did do that?
Can we get extra credit points where it's like?
No,
what
it's
are you
on the
gonna
final.
do this summer? I mean, what are you gonna do? This
Oh yeah,
winter?
Miss York did that one time. He said, "What are you gonna do?"
He was like, "What's your
And then you got like
favorite
extra
subject?"
points. She didn't help me anyway.
Whatever. Yeah.
Because you didn't answer it.
No,
Right.
no.
You guys, I need to keep going. Just leave me alone. I want to teach. All right, let's go. All right.
Get on.
Number 8. Okay, we're good. Okay. Are we ready for number 8? Okay, good. All right. So now for here, it's more of an extension of what we just did in the previous example. Your direction angle is 150. So you go 150, just like you do unit circle. So it's all the unit circle convention, right? You go 150. The length is 7/2. I mean, I don't know how to draw 7/2. Just draw a generic vector, whatever, right? It's all good. But my goal is to break this down to its horizontal and vertical components. That's what we do with vectors. And you'll see why that's so critical when we get to example 10, especially for those who are in physics and you're learning about force, right? Free body diagrams, like you're trying to break your force down to like horizontal and vertical components. You have a bunch of forces acting on one object. You got to add up all the horizontal components first, all the vertical components. That's why we got to break it down this way. So when you do this, it's going to be the magnitude times cosine theta. I don't know why my computer's slowing down now. I'm recording this right now because Sarah's not here.
Hi, Sarah.
Sure, you can say hi to her. Here, you can say that.
See if she watches it.
Actually, good way to test her. Actually, that would be. All right. At 8:55. All right. Okay. So anyhow, that's all you're doing, right? So you're just gonna do 7/2 times the cosine 150. And why the cosine for the horizontal? Because cosine is adjacent to hypotenuse, right? The horizontal is adjacent, clearly. So 7/2 times cosine 150.
Do like cosine 30.
No, because you gotta have to keep it negative. It's gotta go into the left. And then 7/2 times sine 150. Yeah, what's up? Well, hold on a sec. I can't hear the question. Guys, I can't hear the question. Yeah. Oh, so what I'm trying to do is I'm trying to write this. So I'm giving you the direction of the vector, and I'm giving the magnitude of the vector. I want to write this vector in component form. So what I'm trying to do is I'm trying to break down this arrow here into its horizontal. And vertical, meaning I want to know how long it is this way, and how long it is that way. And if you think about the basic trig, right? If this is my angle right here, cosine is this over this. So that's all I'm doing here, because that's like my hypotenuse, the 7/2. The 7/2 is the length of the blue arrow.
Should be negative.
So I'm doing adjacent or hypotenuse. I mean, so if you think about, think about what's cosine theta? Adjacent. Your hypotenuse is 7/2, right?
Wait,
Right.
Wait, what was your error percentage?
That's what I'm doing.
I don't know.
And I do the same thing for the opposite.
Or,
side.
but. 26%.
Okay.
Yeah.
Hey, guys, stop goofing off. All right. So 7/2 times cos 150 is negative.
-3.
Yeah, I think you guys are right. 3.5 times cos 150. Negative 3.031, correct.
Could you technically do 30 and then just like see what quadrant?
And make it negative. Sure. Yeah. And that's going to be 7/4 or 1.75. Because that's sine 150 is 1/2. Yes, Samarth, go ahead.
Decimal. -7 or
Actually, if I do ask for exact values, yes, I would want that. But for the word problems, I didn't ask for that, so I don't care.
What do you do to find exact values?
You're using circle knowledge.
Oh, you know, it's a 36 and 90 triangle, right? So you
Yeah.
you do that.
Well, that is the same thing.
Long way, Storm. It's
It's not the same. It's the same, dude. Rough. Yeah, come on, man. Same. All right. So we're okay with that? All right. Last two problems and we're done. All right. And guys, if you want time to work on homework, let me get through this, okay? All right. Now, example 9 is just like example 8, just we're replacing this vector with an airplane. So the airplane's taking a nosedive, I guess. It's descending at 210, 100 miles per hour. I don't know. It's a good question.
No, it's like classy. I like it. It's like antique.
It is actually.
You
Yeah.
can tell this plane was in World War II.
Sure. Okay. All right. Anyhow, even though it's it says descending angle of 30 degrees, but I mean that's a little vague. So you needed a diagram because it could have been 30 degrees pointing to the right, but whatever. But we are going to talk about direction, like in terms of like a compass, like north, east, south, west, or bearings. We're going to talk about that today and tomorrow. Anyhow, oh, and by the way, I have a packet on vector word problems, which I'll hand out to you guys tomorrow. It's a really nice, fancy packet. Because word problems are going to be a big part of vectors, and we're going to explore that for example 10 for sure, and on the homework. Anyhow, for this one's pretty easy. If you want to break this down to its component form, you're going to do its magnitude, which is 100. So speed is always magnitude, right? So as we talked about, like, yes, you consider your velocity is negative 50 miles per hour going north in El Camino, but the cops are going to say, no, you're still going 50 miles an hour. So speed is magnitude, right? Speed is always magnitude because you drive 50 miles per hour regardless of what direction, it's going to be dangerous, right? If you crash into somebody. So you do 100 times cosine of 210, 100 times sine 210. So again, just an extension of example 8. Graham, go ahead.
Instead of sine 210, you just say sine 30.
Yes, we make it negative afterwards. Correct. Yeah, Simone just asked that also. Yeah. Well, I pay attention because I know what you guys are asking. So anyway, negative 86.603. And the last one's going to be negative 50. Okay. So this matters tremendously for the next example, because what we're going to do is we're going to take a look at an airplane, another airplane in example 10. But we have to understand the plane is pointing west and south, right? This plane is definitely going the southwest direction. So we're going to talk about like, direction in terms of like compass and whatnot. But that matters a lot because there's a bit of a westerly direction, if that makes sense, a bit of a southern direction. So you see negative for X, negative for Y. But what if this plane encounters some wind? What if the wind is blowing north? If the wind's blowing north, clearly this plane's gonna divert a little bit and go this way, right? Or what if the plane's blowing, sorry, what if the wind's blowing east? Then it's gonna slow down a little bit. It's gonna, it's gonna take longer to get to the destination, right? Or what if the wind is blowing west? Then you get to your destination faster, right? So we have to take that in consideration because that's what real life is like, right? So now, anyone in here play golf?
Do.
Okay, wind matters. Wind can matter a lot when you play golf, right? If you're going with or against the wind, right? That can even in football, like if you have or baseball, so that happens sometimes too, right? So those are actually, I think, cooler examples. But let's talk about this airplane here. All right. Now, okay, I really need you guys to focus because this is a little confusing. Guys, Arav, can you focus, please? Thanks. All right. So there's something called bearing. It's a little confusing, and I don't know how this came about, but we'll just go with it. So, and there's actually another one that involves like south and west and east and north. I'll do that with you guys tomorrow. But for bearing, the way this works, if you assume you start north and go clockwise, so the airplane has a bearing of 330. What that means, if you start here, so you start in the north direction and you go 330 clockwise, tell me when I should stop.
Keep going.
Keep going.
Stop.
Okay, good. All right. Good. All right. So for example, what would this angle be right here? Good. W30, right. Radians has no place. We want to keep it. It's easy to use degrees because we can visualize degrees more easily than radians. So yeah. So it's easy to use degrees. Even though pilots are good at math, but it's good to use degrees.
Degrees on this test.
Of course, yeah. Okay. So fine. That's what we have, right? We'll worry about the math later. Now let's look at the wind. And by the way, this is the airplane's direction and speed if there was no wind. If it was flying in still air, fine, you direct the airplane that way. Say, for example, you're flying to I don't know, Alaska, right? So you leave San Francisco, flying to Alaska. Alaska's kind of a little more off over there, right? So great. You're flying that way. However, there's a wind. The wind does this. Now, what's this direction angle? Direction angle, it's like unicircle. Okay, just so you know, direction angle is like unicircle. We've already talked about that. What do? Positive x-axis, counterclockwise. Just like we've always done, right? So 45 degrees. So the wind is going to do this. So the wind is clearly blowing to the east and north. So as you can imagine, when this wind counteracts this airplane, it's going to blow a little bit more to the right, but it's going to go up even more. So maybe we're flying to Seattle or Vancouver, right? Fine. So that's fine, because if you're going to fly to Seattle, Vancouver, the wind's blowing this way, you would direct your airplane more to the left, because the wind's going to blow you more to the right. So you have to take that in consideration. And in fact, actually, if you want to add these vectors, it would kind of look like this, right?
No.
They have computer systems that do it all for them. But pilots got to know their math really well, and they probably learned this stuff. I mean, a lot of pilots have like engineering backgrounds, so. Anyhow, this is what's happening. Airplane, wind. So I want the combination of those vectors, right? I want to add these vectors because when I add these vectors, will that give me the final result?
Yes.
And that's why it's called a resultant speed. That's why we call it resultant vector. It's a result that happens when you combine multiple vectors. So this right here is going to be the combination of both airplane and still air and the wind. This will be air plus wind. Airplane plus wind. So how do I do this? I need to break down each vector into their components. That's the only way I could do this.
Addition.
And you have to add the two vectors. That's why we have vectors. Now, because you're asking, why do we have vectors? That's the reason why. In physics, if you're like if I'm pushing on this little podium and Catherine's pushing on, someone's pushing on, we're like playing tug of war or whatever. I don't know. Or any of you guys watch Squid Game? Yeah, you know that one crazy one where like they're like playing tug of war and like you have to, yeah, it's gruesome. Actually, it's really terrible. I shouldn't be talking about this at school, but you know, like they're pulling on each other, right? The forces. That's vectors, right? That's 100% all about vectors. And if one is pulling another way, you add those vectors, and it goes a certain direction, right? So that's exactly what's happening here. So let's do a vector for the airplane. Let's do a vector for the wind, and let's add the vectors afterwards. Okay. So airplane.
It's like 180 plus 30.
So airplane. We're gonna do this. Okay, now
150.
the magnitude of the airplane is 500. However, I'm gonna do this. Let me erase some stuff here. It's getting a little too busy. I'm gonna do this, guys, for the when you do the vectors, always use direction angle because it's gonna make your life much easier to do the calculation. What is the direction angle for the airplane? We know the bearing is 330. What's the direction angle? 120. Use that instead. Yeah, use that instead.
So.
Okay, so that should be negative 250, comma some wacko number.
These are all 433.01.
433.013.
127.
By the way, I really want you guys to practice precision because, you know, as you know, if an airplane's just a little bit off, if it's got to fly to Seattle and it's a little bit off, maybe it's going to land in Idaho or Wyoming or somewhere else, right? So you want to be careful that you're precise, right? Yeah. Because that was 330. So it stops short of 30 degrees for the positive y-axis. So you go 90, then extra 30. That's why. Yeah. Good question, though. No, you should need to ask that. Okay, wind. For the wind, that was 70 times cos 45 degrees. 70. Yeah, they should be the same, of course. And that's going to be, what's that going to be? 70 cos 45. 49.497. And 49.497. Okay, so you got this vector. And you got this vector. So guess what we're going to do? We're going to add those two vectors. Those two vectors will get me the result. So I do need a little bit of space. I'll clear this up here. So when I do, and we'll call this just for sake of making things easier.
Yeah, I don't think so.
Let's call this vector A and vector W. Okay. So we have both vectors. That's going to be that plus negative 250. So that should be negative 200.503. That's a decimal point. Sorry about that. And then that plus the other guy, 482.510. 5, yeah. Okay, before I go any further, to finish out the problem, you guys see what I just did? I had both vectors. I had this vector, this vector, this vector, this vector. Or sorry, this component, that component, that component, that component, right? So it happens that, yeah, sure, it's gonna go a little less to the left now because this is blowing a little more to the right. So if this is going initially -250 to the left, okay, now it's gonna be blowing a little more this way, but it's definitely getting more of a push in the north direction, right? It's getting more of a push in the north direction because the wind's pointing north. So if I want the speed of the final airplane, what am I going to do about this new vector? Magnitude, yes. So my speed is going to be the square root. I can erase this up now. The speed is going to be the square root of that junk. Added and squared, all that junk. Which should be, let's see here. Square that plus, there's nothing to simplify because it's all decimals.
Should we just divide the decimals or no?
What do you mean by divide decimals?
Like,
this is
it's
what
like
we-
over 5.
But then like if you divide it, then like that's it.
Wait, what?
Like if you put it over the magnitude, like you get the fraction, but then
Wait,
you divide
no,
it.
no, we're not, why are you dividing by the magnitude?
Oh, okay.
That'd be a unit vector.
Oh, are we not doing?
No. We're just finding. No, you're doing more than you need to, Captain. No, you don't need to do that. No. We just want the magnitude. That's it.
Oh,
Yeah. What did you get for the magnitude? You got it. What was it?
520.
Yes. Just leave that alone.
Okay.
Don't do anything. Yeah. That's good. You found the unit vector, which we could. I mean, that doesn't do anything for us necessarily.
What would like pilots use the unit vector for?
That's another thing we're going to talk about next week. Because we're going to talk about something called projection vectors next week. So just hold on to that thought.
Hey,
That's actually a pretty good question, Rob. Congratulations. Yeah. Okay. So 522.511 miles per hour. That makes sense because it should gain some speed, right? It's going 5 miles per hour, and the wind's helping it move faster. So yeah, it should be going a little faster. It makes sense, right? So that's the magnitude of the airplane with the wind. And then the direction, because now it's not going as much to the east, it's going a little bit more pointing towards west. So to find a direction, how are we going to do that? Well, hold on. I need first to find tan theta, right? Yeah, let me erase the other stuff here because I'm running out of space here. Okay. Tan theta is 482.510 over -200 let's get the decimal equivalent of that. What's that going to be? That divided by -2.407. So clear this would be in a calculus section, by the way.
will there be a non-calc section for this set?
Great question. Maybe no, because tomorrow some of that's non-calc stuff. I don't know yet. I haven't thought that far ahead. You should get -67. Oh yeah, there we go, 67, right? Okay. Number should seem to show up a lot. 0.435 degrees. But you're not going to say that as your answer though. Right? Because if you say that as guys, pay attention, please. If you say that, you're not going to Seattle or somewhere in the Pacific Northwest. You're going to Phoenix or Cabo. Maybe it's a little nicer. I don't know. Or Mexico City or
We should do a field trip.
Nicaragua. I don't know.
Just you period though.
You guys already go on spring break. Yeah, there's a school field trip to Cabo every spring break. Come on. Let's not, yeah, I don't know. You guys go everywhere. So, all right. However, What, I know it is. What are we supposed to do? Add 180, right? Supposed to add 180 to that. That's the true direction. Add that to 180. You should get 112.565 degrees. And if you think about that, does make some sense because it is going to be pushed a little more in that direction. Should be closer than 90 degrees. That makes sense. So yeah, I feel good about that. I mean, it's not much. I mean, it was 120 initially, but then because the wind kind of blew it a little more this way, so that makes sense. So hopefully this visual gives you a firmer understanding of vectors. And we'll expand on this more tomorrow and next week. Well, I like that. That was a nice pun. You said you came with that?
I did, yeah.
Yeah, that's good. That's all right. I like that. So it blew him away. Oh, yes, you got good. All right, nice. Okay, we're good. All right, so we're done with the lesson. Homework is going to be the rest of the packet, 11 through 16. You guys have the answer key to check your work, okay? And that's all you're doing, just 11 through 16. That's the homework, okay? All right, so we're all done. All right, good. Good lesson today.